Our objective today for our experiment was to see whether adding more mass to a small cart with wheels would affect the amount of ground it covers. By adding more mass to a small cart and measuring the distance it traveled, we were able to see how weight influences motion.
To start off, we decided to make a 30-gram handmade cart. We decided to keep it lightweight so then by adding the weights later it would show the difference. For the track, we used an inclined ramp and the most important part here was the resting area at the top. This made sure that the cart always started at the exact same height so the test remained fair. To change the weight, I used 650-gram masses, but I didn't just guess their weight. I used this gram scale or digital scale to weigh the cart and each individual mass. This allowed me to be more precise and know exactly how much total weight was rolling down the ramp after every single trial. Next is the measuring tape. We chose this because it's flexible and it's long and it can be laid out flat on the floor, starting right from the starting point from the bottom of the ramp to where the car stopped. This allowed us to record exactly where the car stopped down from every last centimeter. So now, how did this all work together? By using the scale to measure the weight, the ramp to provide the energy, and the tape measure to track the distance, we were able to gather clear data. Each piece of equipment played a specific role in making sure my results were accurate and easy to compare. Now let's look at what actually happened during the test.
Good day, everyone. My name is Delaney Fairweather, and I have been tasked with explaining our table to you guys. Our table is showing the initial, final, and the different trials with the average distances. Let us start with column 1. It shows our initial mass, which was measured in grams with the help of our electric scale. You may be wondering, as you have looked at our materials, you may have noticed that we used 50-gram weights, and the cart weighed 39 grams. So, how does 39 plus 50 equal 88? Well, this is just because of mass deficit, which is the difference between a mass of an atom's nucleus and the total mass of an individual's protons and neutrons. We will now be moving on to the precautions that we have taken to ensure no bias was at play for this entire experiment. So, what we did was picked an area that had little to no wind currents to minimize external force moving the car, and we conducted more than one trial to ensure no bias is at play. For our sources of errors, we came up with the conclusion that we might have released the cart at different moments, which had caused different results on how far the cart traveled, so it caused it to be biased. And it improperly reflected how added mass increases or decreases in distance. For our limitations, we came up with the conclusion that if any of the weights were damaged or had any deformities, there wouldn't be a true reflection of how far the distance traveled is according to the weight.
One possible source of error in our experiment was the release of the cart. But why? If the cart was released at slightly different moments or with different amount of force, it can affect the amount of ground it traveled on. This can affect the results by having the results become biased or not reflect the true effect of adding more mass to the cart and the amount of distance it traveled.
One limitation of this experiment was the weights used on the cart. If any of the weights were damaged, this could affect how the mass was distributed on the cart. When the mass is not evenly placed, it can change the way the cart moves as it travels down the ramp. Because of this, the distance may not be accurately reflected on the effect of the mass alone. Instead, the movement could be influenced by imbalance causing the cart to veer slightly or lose moment. This means the results may not be completely true representative of how the weight alone affects distance. Although care was taken to use the same equipment throughout the experiment, the limitation shows that the condition and quantity of materials can affect the experimental accuracy.
Okay everyone, so for this part of the video, we will be going over the value graphs. Now, these graphs just simply show our data earned from this experiment. Now, the graph on the left actually shows us the data from each trial, whereas the graph on the right shows us the average data, which is just each trial added together and divided by 3. Now, here as we can see for trial number 1, please, pretty please. Okay, here, see, as you can see for trial number 1, for 39 grams, we actually got a total distance of 0.64 meters. Then at 88 grams, we got a distance of 1.05 meters. At 138 grams, we got a distance of 1.84 meters. At 188 grams, we got a distance of 2.12 meters. At 238 grams, we got a distance of 2.98 meters. And at 288 grams, we got a distance of 3.15 meters. Now, unfortunately, due to limitations in our experiment, this is the limiting point. So from here, it just decreased at 338 grams to 2.83 meters. And this is a trend we can see in each trial, where at 288 grams, the distance decreases due to the limiting point. Now moving on to trial number 2, we can see here that at 39 grams, the cart traveled 0.38 meters. At 88 grams, the cart traveled 0.81 meters. At 138 grams, the cart traveled 1.55 meters. At 188 grams, the cart traveled 2.65 meters. At 238 grams, the distance traveled 3.05 meters. And at 288 grams, the cart traveled 3.16 meters. And then it broke down all the way to 2.56 meters at 338 grams. Now here, on the final trial, trial number 3, we have 39 grams, making the cart travel 0.47 meters. At 88 grams, the cart traveled 1.40 meters. At 138 grams, the cart traveled 1.68 meters. At 188 grams, the cart traveled 2.63 meters. At 238 grams, the cart traveled 2.92 meters. At 288 grams, the cart traveled 2.78 meters. And at 338 grams, the cart traveled 2.05 meters. And that sums up all 3 trials basically. And as you can see here, on the vertical axis, we have all of our lengths. Now here on the horizontal area of the graph, right down here, you can clearly see the initial mass, otherwise known as the mass of the cart, was 39 grams. However, when a mass of 55 grams was added, it actually lost 1 gram of mass due to mass defect. Now, moving on, let's go to the average meters accumulated from the 3 trials. So here, as you can see, at 39 grams, the cart traveled 0.5 meters. At 88 grams, the cart traveled 1.09 meters. At 138 grams, the cart traveled 1.69 meters. At 188 grams, the cart traveled 2.47 meters. At 238 grams, the cart traveled 2.99 meters. At 288 grams, the cart traveled 3.03 meters. And at 238 grams, the cart traveled 2.48 meters. Now, all this tells us is the average. So amongst all these trials, these will be the average distance that the cart will travel when these masses are added together. So that wraps up the part of the graphs. I hope you understood. Now we'll move on to the next part. Bye.
Okay, so now that we looked at the data we gathered, the results are very clear. Our hypothesis was indeed correct. As the mass of the cart increased, the distance it traveled increased right along with it. The empty 30-gram cart was our control group, our baseline, and every time we added a 50-gram weight, we saw that the finish line moved further and further back. Why did this happen? This happened because it comes down with momentum. When the cart is heavier, it has more push behind it. Even though friction from the floor is trying to slow the cart down, the extra weight gives it the energy to keep fighting that friction for a longer period of time. A light cart stops easily, and a heavy cart is much harder to stop. So with that, thank you for your undivided attention.